for the part 2, unit 5, part 2 notes video on graphing polar equations. So in part 1, we introduced polar coordinates, and we briefly talked about what a polar equation was. It has your variables of r and theta, and we talked a little bit about converting from rectangular coordinates to polar coordinates, and the basic shape of a line or a circle. So here we're going to get into a little more depth on some different types of polar equations over the next couple of lessons. Today we're going to focus on circles and limacons. Scroll down a little bit here. So for a circle, the equation is going to be in the format r equals a and then sine or cosine of theta. So the difference being if it's cosine function versus sine function, that's going to tell you if your circle moves vertically or horizontally from the pole, okay? So if cosine is the trig function, so r equals a cosine of theta, you're going to have a circle where the a value is the diameter, okay, so all the way across the circle, and that it has its leftmost edge at the pole. So it has moved horizontally. So this one that's pre-printed there would be a positive a value. So the left side of the circle is at the pole, and it's a diameter of a. Now, if there was a negative in front of that a value, then it would be shifted to the left, okay, and so the right side of the circle would be touching the pole. But it's moved horizontally left or right if it's a cosine function. Okay, and in contrast, if it's a sine function, moves vertically. Okay, so the a value is still the diameter of the circle. Okay, and if it's a positive a, the circle is shifted up. Okay, a positive a, so the bottom of the circle touches the pole, and the diameter is a. But if that a were negative, when it's a sine function, then it's shifted down, and the top of the circle is touching the pole. Okay, so this is how you sketch those graphs. So you can see in these examples here, you can tell before we even draw anything that part A of example 1 is r equals 2 cosine theta. That means it's a circle with a diameter of 2. And because it's cosine and the 2 is positive, the circle is to the right of the pole. Okay, and here for B, we can tell it's sine and the a is negative, so it's a circle shifted down, so the top of the circle is touching the pole, and the diameter is 3. And for part C, a is -5, and the function is cosine, so we know it's left or right, and because it's negative, it's left. Okay, so the right side of the circle is touching the pole. So I'm going to scroll down so you can actually see those pictures and get them drawn. So shifted to the right, okay, with a diameter of 2. Shifted down with a diameter of 3, and to the left with a diameter of 5. That's how you would sketch those circles. So those are basic polar equations for circles. We talked about a circle yesterday centered at the pole. When you just have r equals a number, you don't have an angle, then it's equidistant all the way around from the pole, and it forms a circle with the pole as the center. Okay, so these are a little different because they have r and theta. They have both variables, so it's not centered at the pole, but it is touching the pole. All right, now limacon, this I wrote here how you pronounce that, limacon. That's French, if that pronunciation is confusing to you, is got several different variants of limacons. When r equals a plus or minus b sine of theta or cosine of theta, we know that it's not going to be a circle anymore because there's a value being added or subtracted. It's not just something times sine or cosine. There's also something being added or subtracted. Okay, and the limitations are that the a value has to be greater than 0, and the b has to be greater than 0. Okay, so it can be a plus or a minus there, but the b value itself and the a value itself has to be greater than 0. All right. Now, depending on what that a and b value are, will help determine the shape of the limacon. Okay, so you've got this table, okay, yours is not filled out, and I know it looks confusing with it all filled out at once. So we're going to go one column at a time here. You look at the ratio of the a value to the b value of the number out here that's being added, the constant, versus this number in here being multiplied. Okay, so when you do the ratio a over b, if that is less than 1, that means that the a value is less than the b value, is when this happens. So if a is less than b, that's going to be a limacon with an inner loop. Now, if the a and the b value ratio is 1, that means that they're equal to each other. That's going to form what's called a cardioid. If it's somewhere between 1 and 2, so it's like 1.2, 1.3, 1.4, etc., that ratio, that means that the a value is bigger than the b value, but not twice as big. Okay, it's bigger than b, but not twice as big as b. Okay, when that's the case, we have what's called a dimpled limacon. Now, if the a value is bigger than twice b, it's more than double, it's double b or more, okay, then you have what's called a convex limacon. So here are the pictures of those for you to sketch for your examples. And just like with a circle, whether it is a sine function or a cosine function determines if you draw the limacon vertically or horizontally. Okay, so you can see in red here all the sine examples. These are all drawn vertically. They're going up from the pole. Now they could also go down. That'll depend on some positives or negatives. And then cosine is going to go horizontally from the pole. And all of our initial examples are being drawn to the right. All right, so a limacon with an inner loop. So you can see the picture here. There's an inner loop, okay? We're going to talk more about the steps of graphing these and plotting points and then connecting them to create these shapes, okay? But you can see this one has an inner loop, okay? A cardioid comes in here, and it kind of looks like this one looks like it's upside down, an upside down heart. Cardiac has to do with your heart, your cardiovascular system. Okay, so that might help you remember the shape of a cardioid. Okay, it's kind of heart shaped. And then a dimpled limacon, okay, doesn't quite come to a point in here like the cardioid. It dimples in and curves back out. This one kind of like the shape of a bean almost. Okay, now the dimple doesn't have to be real pronounced. I drew it a little more pronounced so that you could see the shape, but sometimes it just barely comes in a little. So that's a dimpled limacon, the difference between dimpled and cardioid. And then if it comes in inside itself, then that's when it creates the inner loop. And then a convex limacon, these are all concave, they're coming in. Okay, notice here when you get to this side of the limacon, it never curves back in. Okay, it's got an outward curve. That's convex. Okay, but this is not a circle. Okay, you can see this side is much higher than this side. Is not circular. It is still a limacon, even though it's convex. And it's not an oval. Okay, it's a special shape. Kind of looks like, I don't know, I compared that one to a heart and a bean. I guess maybe a rock. I don't know. Kind of looks like Patrick's rock in SpongeBob, maybe. But so that's the general shape of those limacons. Okay, so we're going to look at some examples to get an idea of how we come up with those given equations. All right, so I should take a second to fill in these steps, and then we'll go through these examples down below. So your first step is to determine, is it sine or cosine? Because that's going to tell you, like I said, is it vertical or horizontal? Okay, and then you compare the ratio of A to B to get the shape. Is it going to be, is it going to have an inner loop? Is it going to be a cardioid? Is it going to be dimpled, or is it going to be convex? Okay, once you know what shape it will be, then we start determining the features. So we add A plus B. That's going to give us the height along the main axis. And then the main axis is determined whether it's vertical or horizontal. Okay. The A value itself is going to tell us the stretch, or you can think of it as the width along the opposite axis, not the main axis, in both directions. And then A minus B, so the difference, is going to give us the lower point to plot. Now, if this comes out as a positive, okay, you're going in the opposite direction of the height. And if it comes out negative, you're going in the same direction of the height. Okay, so let's work through those steps and some examples. You can see them at play here. And I know I have all three of them there. I'm actually going to do this to try and look at just one at a time here, though, so it's a little less confusing. So let's look at just part A right now. So I determine its cosine. So I know that it's going to go horizontally. Okay, now the A to B value, A is less than B. So that's going to be an inner loop. So we're going to have a limacon with an inner loop because A is less than B. The ratio of A over B is less than 1. I'm going to do A plus B. So 1 plus 2 is 3, because we are the plus or minus in the middle there. Okay, that tells us the direction. That goes with the cosine there. That's how I know it's going to be to the left, because that negative. Okay, but the actual B value is just 2, and the actual A value is just 1. Okay, so 1 plus 2 is 3. That's going to be the height. Now the A value is 1. That's that stretch, or the width, along the opposite axis. And then A minus B, so 1 minus 2 is negative 1. Okay, and that's going to be our lower point. Okay, so I tried to color code those in the picture here. So we know our main axis is the horizontal, the x-axis, because of cosine, and to the left for our height of 3. So from the pole, I go 1, 2, 3, and that's the green point there. Okay, along the opposite axis, the width was 1, because that's the A. So in both directions, so I go up 1 and plot a point, and from the pole I go down 1 and plot a point. So those are the two in orange. And then the lower point, the difference from A to B was negative. So that's what I was saying up here. Oh, I think I have to close this real quick so I can scroll up. Because that came out negative, we go the same direction as the height. And we knew that because it's an inner loop here. We knew it would have to be coming in toward the top of the limacon. So we go in 1. I hope that makes sense. So I got the green point, and then I got the orange points, and then I got the blue point, and I told myself I knew it was an inner loop. Okay, so then I sketch across over itself here at the pole, go out this wide and come up across the top back through. And that tells you kind of how wide it should be here, and an inner loop to that last point. All right, now when we look at B, cover this up again. Cosine again, negative again. So I know it's left. So it's a horizontal to the left. So we know the top of the limacon is actually going to be on the left side. Now, there is no number in front of cosine. So that's an understood 1. Okay, so it's 2 minus cosine theta. That means A is 2 and B is an understood 1. So 2 is double 1. And we said when the A value is double the B or bigger, that's when it's going to be convex. So that tells us the shape that this should be. It's going to be just like that rock shape. And then when I add them, 2 plus 1, I get 3 for the height. Okay, so same thing here, that green, the top of the limacon's at the same spot. The stretch this time is 2, because B is 2. So I go from the pole up 2 and down 2. And then the difference, A minus B, 2 minus 1, is positive 1 this time. So it's a distance of 1 still, but since it's positive, you're going in the opposite direction as the height. Okay, so the height was to the left, so this is to the right one. And that's what makes it convex. Okay. All right, and then last but not least, this one is sine, so we know it's vertical, and it's negative here, so it's going to be going down. So it's going to be an upside down limacon. Now, the A value is bigger than the B, but it's not double. 3 is not double 2. So that ratio is between 1 and 2. So we know it's going to be dimpled. Okay, so a dimpled limacon, vertically going down. The A plus B gives us our height, which is 5. So that means from the pole, I go down 5. That's going to be the top, per se. Because it's negative, it's going down. It looks like the bottom of the dimpled limacon. And then A is 3. That gives you the stretch, okay, or the width to the opposite direction. So left and right 3 to get those orange points. And then A minus B, which is 3 minus 2 is positive 1. Okay, so in the height went down, so I go in the opposite direction since it's positive 1. But I know when I connect these, I don't just connect it convex like I did this one, because we're told based on this ratio that it is dimpled. So when I sketch it through those 4 points, I know when I'm coming through those orange ones, I have to go up past the blue. It's going to go up higher than the blue point and come back dimple into it. Now, I'm just sketching these. These are not perfect. I'm getting 4 points and drawing the general shape. So I don't know exactly how high these are without doing some other calculations, which we're not going to do right now. We're just getting general shapes right now. Okay. All right, so that's the steps that you need to follow to be able to graph limacons. Now, let me get off that. The next one is supposed to be one for you to try on your own. So I know you're watching this on a video since I'm out sick. So pause the video for a sec, give it a shot, and then unpause to come and check your answers. All right, so the one you were hopefully able to try on your own is sine, and it's positive. So it's vertical, so that means our height is going to go up because it's positive. Now, the A value is less than the B value, so we know that's going to be an inner loop shape. A plus B is 3, so I go up 3 from the pole for that top point. And then for the width, A is 1, so I go left and right 1 for those orange points. And then the difference, A minus B, so 1 minus 2 is negative 1, and that's the lower point. So it's a distance of 1 from the pole, and since it's negative, we go in the same direction as the height, which was up. So we go up 1, okay? And then we can sketch through those points. It loops in on itself and comes around like this. So hopefully you did okay with that one. I got some of those parts right, if not all of them. All right. Now, this is just a quick little calculator explanation so that you can see what it looks like in the calculator, how you can check in the calculator your work. At the end of this unit, we will actually be doing a project for our major grade instead of taking a test. And we will be using the calculator a lot for the project. So you really do need to understand the settings in the calculator. So you can see if I go into mode, where I can change from radian and degree mode. Okay, I'm going to set this in degrees. I'm going to do, it's going to be easier for me to measure it in degrees. And then underneath that is the function mode, parametric mode, polar mode, or sequence mode. And we are doing polar, okay? So it's the type of equation. Typically, anything you've done on the calculator has been in function mode, but you need to switch it to polar. So degree and polar mode, okay? And then you go to second window to do your table setup for your graph. And we want to change the table set to the change in table, I should say. That triangle, that's a delta symbol. That means the change in the table. When you go to it, you want it to count by 15, so every 15 degrees. Okay, if you leave it counting by ones, which it standard setting is to change by ones, you're gonna have to do a lot of scrolling to get enough points there. And it's going to take a while in your table to scroll through and see all those points. So we'll change that to 15. Then you can go to y equals, the button y equals, it's actually in polar mode. So when you go to that, it's actually going to show up as r equals. It'll have a r instead of a y here. Okay, and then you type in your equation and you use the same button for x to get theta. You'll notice the button on the calculator, it has multiple variables there. And when you're in polar mode and you push that button, it automatically shows up as theta. Okay, so our equation was 1 plus 2 sine theta. So I enter that, and I can go and look at the table to get points to plot. If I'm graphing this by hand, I can see there's a point at 0 degrees, 1. So that's at 0 degrees over 1. So that was one of those width points that I had plotted in orange. Okay, I can see at 90 degrees, I'm at 3. That was that top point. Okay, at 90 degrees, it's 3 units out. And then I could keep scrolling and get the 270 and the 360. Those are the only 4 points I plotted, was at 0, 90, 180, and 270. Okay, to get all the points in between to actually see how wide this should be or how low these points should be here, you can look at all of these points in between those quadrant angles as well. Okay, and compare that graph to what we graphed here. So it actually comes out quite a bit wider than we made it out to be, but that's what happens when you only plot 4 points. It's not going to be totally perfect, but that's how you can input it into the calculator. Check the modes there and get your table set up and type your equation in. All right, so that's it for that set of notes. So you should have time to go and finish the Delta Math assignment or start it if you didn't get started on it already yesterday in class or at home. I did want to point out I made a little separate add-in page to our notes. This is not in your notes packet, but I thought it would be useful to have as a kind of reference for graphing polar equations in the calculator. And this in color, like this, is in It's Learning. Oh, great, I got kicked out. Sign back in. Yep. Sorry, I had this pulled up, but I guess I let it lapse and kick me out. All right, so if you're in the unit 5, you may have noticed I actually put it in 2 places because I didn't know where y'all would instinctually look. I put it in the note outline underneath part 1, 2, 3, 4. I added the calculator page, but I also put it in the completed ones because it is complete. There's nothing you need to add to it. Excuse me. So here at the top of the completed notes page, you can see the polar equations and the calculator as well. I'm not going to print that for everybody because I didn't get it in the packet and I don't know if you'd want it to look at anyway. And if you do, it's here online. If you want to print it, you're more than welcome to. But our printer at school wouldn't print it in color anyway, and I think it's better for you to look at it in color to see the highlighting. All right, so it talks about making sure, going to mode, making sure you're in degree and polar mode, and then going to second window and setting up your change in the table to 15. And then it goes into a little more detail. If you push the window button right here next to y equals is the window button. Okay, you get this little image on your screen. Now, if you want to set this up to center to fit most of your graphs, you want to change your theta minimum and maximum to 0 to 360 and change the theta step to 1. Okay, that should be our standard in degree mode to go around 1 loop. If you keep going past 360, you just keep hitting the same points over and over and over again as you go around. So kind of, same thing we did on the unit circle. You just keep going round and round through whatever the shape is. So change that 0 to 360 by ones. You can, and I put this here, change it to 0.1 instead of 1, or 0.01 or 0.001. You can keep going smaller, and the smaller you make this theta step, the slower it's going to graph on the calculator. So if you want to watch it graph more slowly, then make this number smaller, okay? But if when you click graph and you watch the line appear, the curve, I should say, appear to create the shape, if that's not too fast for you, then 1 is fine. But if you would like it to graph slower so you can actually watch the path that it goes, then just make that number a little smaller. The X and Y minimum and maximum, that's going to be according to the size of your graph. So that depends on that A and B value, like what your height and width of your limacon or what your circle's diameter, whatever the shape is. So the X and Y maximums and minimums are going to vary, but you do want to make them the same. Okay, so if you make the max 5, make the min -5. You want them to, because you want the pole to still be in the center. Okay, so I would still make them equivalent so the pole is centered. All right, now if you go to graph or second graph, and that's how you're going to view your table or your graph. Okay, so this is just an example of this one plugged in, and what you can see, I have it the change in the theta on the table set to the 15 degrees. And I could scroll down to see all the way to 360 degrees if I wanted. But this is positive cosines, so it's to the right. A is less than B, so it's an inner loop. You can see the sum is 3, so that's where the height is. The difference is 1, so that's the width there to those points on the axis is 1, -1. And or excuse me, that's not the difference. A is 1, so that's why that's 1. The difference is the inner loop comes in 1 because that difference is 1. And if the difference is negative is why it went the same direction as the height. Okay, So I hope this little reference sheet helps because it's not really in the notes how to do that in the calculator really. Okay. All right, so there's that last example shown in the calculator if you want to jot any of that down, or just try it in your calculator to make sure you've got the hang of it, you can. But other than that, that's it for those notes. Okay, so circles and limacons, this chart here should come in handy about the shape and how A and B compare to each other to tell you which shape it should be, okay? And then those steps here are going to be real important. Follow those steps for when you're sketching your graphs. You're doing some of the delta math so you did some of it based on yesterday's notes with the polar equations, but then one of the sets of problems is graphing. If it is not a circle or limacon or line that we've talked about so far, just skip that problem, okay? If it is a different shape, it's a rose, which we'll talk about next week, or a lemniscate or something, just skip that one. You know how to skip the problems in Delta Math. Just say show solution, next problem, okay? You only need to do ones if they are in this format equation or for a circle. That's all we've talked about is circles and limacons, and then that basic circle and line if there's no other variable, only one variable in the equation. Okay, so when you get to the Delta Math problems, that's something we haven't talked about yet, just skip those. They weren't separated by shape, so I couldn't eliminate the ones we haven't talked about yet. All right, that's it for today. Tomorrow you're going to finish the Delta Math today, and then tomorrow you're going to have a worksheet to practice on paper, actually sketching them out, because you're not actually doing the sketching on Delta Math. So I also left some paper practice for you. That's what you're going to be working on tomorrow. And then I hope to see you on Monday. All right, y'all have a good day. Have a good day tomorrow, and then have a good weekend.